Dear all, welcome to the fourth lecture from our videos about hemodialysis. I'm explaining and discussing in these videos the different chapters of nephrotube synopsis of conventional hemodialysis. In this lecture, I will talk about the dialysate circuit. In the previous lecture, we discussed the water treatment unit, and now we will discuss how the pure water that is formed by the water unit will be used by the hemodialysis machine to make the dialysate. In the description of this video in YouTube, below the video, you will find some important links. The first link is a link to this same lecture, but in Arabic language, for those who like to watch the lecture in Arabic. You'll find also a link to the playlist of video lectures about this book. You will find the link for the English playlist and Arabic playlist. You'll find link to download this book for free. You'll find link to download the PDF of this lecture for free if you like to use it. You will find a link for my website nephrotube, nephrotube.com, where you will find more lectures about nephrology than hemodialysis lectures. And finally, you will find a link to nephrotube social media accounts, the WhatsApp group, the Telegram channel, the Facebook group. You can join us to be always updated by the activities of nephrotube. And finally, it's better to subscribe to our channel and to make the notifications on from our channel, so you will be notified once we upload new lectures. At first, I want to mention that the main two components of the dialysate circuit are the concentrates and the dialysate delivery system. We will discuss each of them separately in details. This is my talk outline, and I will start by the concentrates, or we can call them also concentrated dialysate. It is the first component of the dialysate circuit, and the main idea to have the dialysate in a concentrated form is to decrease the bulk and transportation expenses. We mentioned last lecture that the patient may use about 120 liters of dialysate. So it is not logic to prepare this large volume of dialysate in the factory, then transport it to the hemodialysis unit. That's why the dialysate is formed in a concentrated form. This concentrated form is easily to be transported, and this concentrated form will be used by the machine. The machine will mix this concentrated dialysate with the pure water to form the final diluted dialysate. We have two concentrated dialysates that are connected to the hemodialysis machine. The first one is the acid concentrate, and it is also called A concentrate, A for acid, and the bicarbonate concentrate, and it is also called B concentrate, and here B is for bicarbonate. The acid concentrate that is connected to the machine is formed of acidifying agent, and I will talk about the different acidifying agents that can be used in the acid concentrate, and it also contains sodium, chloride, calcium, magnesium, potassium, plus minus dextrose. The acid concentrate is available in both liquid and dry form. This is one of the liquid forms we use in Egypt. In Egypt, usually the acid concentrate is present in the liquid form. You can find here it is formed of sodium, potassium, chloride, magnesium, and acetic acid. Acetic acid is one of the acidifying agents that can be used in the acid concentrate. And it also can be available in a dry form. And this dry concentrate should be dissolved in treated water, then it will be connected to the machine. Regarding the bicarbonate concentrate, sodium bicarbonate is the main buffer used in hemodialysis. There are other buffers that I will talk about them later on within few slides, but the main buffer that is used now in hemodialysis is the bicarbonate. The bicarbonate is available mainly in powder form. Okay. Regarding the powder form of bicarbonate, the powder form itself can be present in one of three forms. One of them, that the powder is usually pre-filled by the manufacturer in cartridge, and this cartridge will be attached to the machine, and the machine will dilute the bicarbonate in it. Here, an example of one of the cartridge that are available. A lot of cartridges can be available. This is an example, the bicart. But there are other forms of bicarbonate as a powder rather than this pre-filled cartridge. At some centers, they may have bags of bicarbonate that is manually mixed with appropriate quantity of pure water manually inside the hemodialysis unit itself before it is connected to the machine. In some other centers, they may prepare the bicarbonate centrally, a central area where the bicarbonate is prepared by mixing this powder with water in central containers. Then the diluted bicarbonate will be distributed to the hemodialysis machines. It is important to know that the manual preparation of bicarbonate, whatever the method, can lead to bacterial contamination, as bacteria thrive in this type of environment. That's why it is important that any bicarbonate solution that has been prepared, not that in the pre-filled cartridge. I am talking about the prepared bicarbonate in the hemodialysis units. So any bicarbonate solution that has been prepared manually or in the hemodialysis unit must not left unused for prolonged time for more than 4 hours. The question now, why the bicarbonate, the concentrated bicarbonate, is separated from the A concentrate? We'll find the acid concentrate in a separate canister, and you will find the bicarbonate in a separate cartridge, for example. This is because if concentrated bicarbonate is mixed with acid concentrate in the same canister, this will lead to the formation of calcium carbonate and magnesium carbonate, as the sodium bicarbonate will react with calcium and magnesium, and this will lead to precipitation of calcium carbonate and magnesium carbonate, and this is not accepted. Another point that I want to mention, you mentioned here that sodium bicarbonate is the main buffer. Is there any buffer rather than bicarbonate? The answer is yes. Lactate containing dialysate, lactate instead of bicarbonate, this is used in the next stage machine, and this is used mainly by home dialysis. In the past, they were using acetate containing dialysate. It was previously used instead of bicarbonate. The acetate is metabolized by the liver and skeletal muscle to form bicarbonate in the body, but it is not used now anymore because it may cause, it actually cause headache and hypotension. Before going to the acidifying agents, I want to say that the machine will take apart a ratio or a part from the acid concentrate and a part of bicarbonate concentrate, and mix them later with water to form the final pure dialysate that I will talk about later in this lecture. We mentioned that the acid concentrate, the A concentrate, is containing acidifying agents. First of all, why we are adding an acid to the A concentrate? This is the same idea why we are separating the acid concentrate from the bicarbonate concentrate. We are adding acid or acidifying agent to the acid concentrate because later on I mentioned that later on the hemodialysis machine will mix acid concentrate with bicarbonate, and again this may cause calcium carbonate and magnesium carbonate precipitates. So the addition of acidifying agent will cause the formation of carbonic acid after mixing of the two solutions, and this carbonic acid will maintain the final pure dialysate pH between 7 and 7.4, and this will prevent the formation of these precipitations and keeps the solution dissolved. The question now is, what are the acidifying agents that can be used in the acid concentrate? The first one is acetate. So the acidifying agent here is acetic acid, as this example, this is acetic acid. But one of the disadvantages of this acetic acid, as I mentioned, that it may cause vasodilatation and hypotension, and may activate inflammatory proteins. But this is the used acidifying agent here in Egypt, actually. Again, take care. We are using acetic acid here as an acidifying agent in the A concentrate. But in the past, they were using acetate instead of bicarbonate in the B concentrate. Okay, so now we are not using acetate instead of bicarbonate, but we are using acetate as an acidifying agent in the A concentrate. The other acidifying agent that is used, and actually it is the preferred if it is available, is the citric acid. One of its main advantages that it reduces clotting, and its disadvantages are hypocalcemia and hypomagnesemia. Now, after we finished talking about the concentrates or the concentrated dialysate that will be diluted later by the hemodialysis machine, I want to talk about types of the dialysate delivery system. We start now to talk about the second component of the dialysate circuit, which is the dialysate delivery system. Actually, there are two types of dialysate delivery system. The single patient dialysate delivery system, and this is the most commonly used around the world, and the central dialysate delivery system. Let's start by the single patient dialysate delivery system. In this system, the treated pure water from the water unit will be distributed to the individual hemodialysis machines. And the hemodialysis machines will take this pure water and take a proportion from concentrate A and a proportion from concentrate B to mix them and form the final diluted dialysate. So at this type, single patient dialysate, the dialysate is formed at single patient station, at single patient hemodialysis machine. But regarding the central dialysate delivery system, that was invented in Japan, and it is mostly used in Japan and some small areas in the world. Here in Egypt, we have about 2 to 3 centers only that are using this central dialysate delivery system. In this system, the treated pure water from the water unit will be distributed to a single central location. This location will mix the water with dialysate A and dialysate B to form the final diluted dialysate. Then the dialysate will be delivered after it is prepared by this central area to the hemodialysis machine. So here the dialysate is formed before the machine, then it is delivered or distributed to the machines. Actually, the central dialysate delivery system has some advantages and disadvantages. The main advantage of this central dialysate delivery system is cost saving. But one of the disadvantages, or two of the most important disadvantages in this system is that if there is any central machine dysfunction in this central area, this will affect all the hemodialysis machine and the dialysis unit will stop working. This is first point. The second point, that in the single patient dialysate delivery system, we can individualize the dialysate composition. For example, if you want to increase the calcium in this dialysate for this patient, you can do this because the machine is forming the dialysate by itself. If you want to make a low dialysate calcium, you can. But here, you prepare the dialysate centrally. You cannot modify electrolytes in the dialysate for each individual. Although there is some updates showing that there are new invented techniques that in this central dialysate delivery system you can individualize the composition for certain patients. But actually, I'm not expert in this type, and it is not famous in Egypt. So I will not talk more about that. We will talk in detail now about the single patient dialysate delivery system. Single patient dialysate delivery system. I want to start by its components. First, I want to talk about the components of single patient dialysate delivery system that prepare pure dialysate. Actually, the preparation of pure dialysate by the single patient dialysate delivery system is done through 3 steps or 3 components: the water preparation system, the proportionating system, and the volumetric control system. Let's go through these steps. This is the dialyzer, and this is the pure water coming from the water unit. We want to form the dialysate so that the dialysate can go through the dialyzer. The pure water coming from the water unit passes through different steps to form the dialysate. The first step, the pure water must be heated. The heater is important to heat the water to a suitable temperature, which is about 35 to 38 degrees centigrade. But it is important to know that as the water is heated physically, the gases within the water will be dissolved and expand and rise on the surface of the water as bubbles. That's why heating the water must be followed by deaeration to remove these gases. We say that the water is deaerated or degassed. This is done by a negative pressure, applying a negative pressure on the water, on the heated water, by a pump to remove these gases. Heating and deaeration of the pure water forms the first component of the single patient dialysate delivery system, which is the water preparation system. This water preparation system, after this water preparation system, the water will go through the second component of dialysate formation, which is proportionating system. In the proportionating system, the machine is responsible for producing the final mixed pure dialysate. The machine will take a proportion of the water and mix it with some proportions of the concentrates, concentrate A and concentrate B. This is an example of the ratios that the water proportionate or mix water to B and A concentrate. So this is the ratios of A concentrate to B concentrate to water. For example, some machines will make according to the canister instructions, and I will show you some examples. The mix will maybe 1 to 1.7 to 42.8. And these, all of them, if we add them to each other, it will form 45. So this mix is called 45x, and it may be 1 to 1.83 to 34. This 38.83x, and there are multiple other ratios all over the world. For example, here in Egypt, if you saw this canister about that is wrote on the A concentrate, you find usually the ratios on the A concentrate. We'll find here our ratio 1 to 35, and 35 here it means 1 to 34. So here we will mix one from the A concentrate to 1 from the B concentrate to 34 for the water. This is another example here from Egypt. You will find it here. 1 liter, this is one ratio. It means 1 liter from the A concentrate, 1.225 from the bicarbonate, and 32.775 from the purified water. And this is the last example here in Egypt, 1 to 36.2. 36.2 is 1 to 35.2. So here 1 from A concentrate to 1 from B concentrate to 35.2 from the purified water. After this, the final pure dialysate is formed after the portionating system. The pure dialysate now is water with mixed ratios from A and B concentrates. And this is the final composition of the diluted dialysate. This is the concentration of sodium, potassium, calcium, etc. pH of the dialysate. Actually, the sodium level and the bicarbonate level can be adjusted and modified through the machine controls and machine settings. You can change the concentration of sodium or bicarbonate in the dialysate through your machine. But regarding, say, for example, calcium, potassium, you cannot adjust their concentration in the dialysate through the machine. But you have to change their concentration. You must have a canister from the start with the concentration of calcium or potassium that do you want. For example, you have a patient that is usually hyperkalemic, and you want to do a low potassium dialysis, so you have to get a canister, a concentrate with low potassium concentration. For example, you have a patient that is usually hypercalcemic, and you want to dialysate against low calcium, to dialysis against low calcium. So you have from the start to get a concentrate with low calcium concentration and so on. But the sodium and the bicarbonate concentration can be adjusted through the hemodialysis machine. After the pure dialysate is formed, it will pass through two monitors, the conductivity monitor and the temperature monitor, that I will talk about them at the end of the lecture in details. After that, the pure dialysate will pass through what is called the balancing chamber before it enters through the dialyzer. The balancing chamber is part of the third component. We are talking about the single patient dialysate delivery system. We mentioned in the last slide, in the talk outline slide, that this system is formed of three components: the water preparation system component, the portionating system component, and the volumetric control system components. The balancing chamber is a part of the volumetric control system, and I will talk about its action and the other volumetric control system parts in the next slide. So the pure dialysate now goes through the dialyzer, and after doing here diffusion and ultrafiltration, the dialysate outflow passes again through the balancing chamber to the drain. Okay. Here on the drained dialysate, there is also a monitor called the blood leak detector that I will mention, and I will talk about it at the end of the lecture. The last point in this slide is that we mentioned that we will talk about conductivity monitor and temperature. Whatever their action, but if the water conductivity is out of the normal range or the water temperature is out of the accepted range, the water will go through bypass circuit to be drained because its temperature is not correct or its conductivity is not correct, and I will talk about these monitors later and about the bypass circuit later on. Now, let's talk about the volumetric control system, where the balancing chamber is part of it. This is our dialyzer, and this is the first two components of the single patient system, which are the water preparation by heating and deaeration and the portionating system. And this is the balancing chamber. The volumetric control system is formed of two parts. The first is the balancing chamber. In each hemodialysis machine, there are two balancing chambers. I am here drawing only one for just illustration, but there are two balancing chambers in the hemodialysis machine acting in alternating circuit. If one is working, the other is in rest, and so on. Each chamber, this is one chamber. This chamber is divided into two halves. And these two halves are separated by a flexible membrane. Okay. Here, the dialysate inflow into the balancing chamber. At the inlet and the outlet of the dialysate inflow, there are one-way valves. These one-way valves guarantee that the dialysate will flow in one direction. Then this dialysate will go through the dialyzer, and the dialysate outflow will go again through the balancing chamber to the drain. And also the balancing chamber has two valves at the inlet and outlet, which guarantee that the dialysate will flow in one direction. Okay, so what is the main function of this balancing chamber? We mentioned now its structure. What is its main function? This balancing chamber guarantees that the dialysate flow and the dialysate inflow and the dialysate outflow will be equal. Because if some dialysate is introduced into the chamber, the fixed deflection of this flexible membrane in the center causes an equal amount of dialysate to get out of it. So, this balancing chamber guarantees that the inflow and outflow of the dialysate are equal. The second part of the volumetric control system is the ultrafiltration controller. Here, there is a side separate line diverge out from the dialysate outflow to the drain directly, and this diverged line contains the ultrafiltration pump. This ultrafiltration pump will get the amount of the ultrafiltered fluid here from the outflow directly to the drain. So, coming out from the dialyzer, the amount of the dialysate and the amount of the water that is ultrafiltered. Here we will get out the water that is ultrafiltered, and here the dialysate will go through the dialyzer. And the balancing chamber will guarantee that the dialysate outflow is equal to the dialysate inflow. The question now, how the ultrafiltration pump acts? Here there is the inflow of the blood into the dialyzer, and here is the blood outflow. There is a monitor for the post-pump arterial pressure, and monitor for the venous pressure, and also a monitor for the dialysate inflow inlet pressure and dialysate out pressure, and all of these send their data to a central computer that controls the ultrafiltration pump to ensure that the ultrafiltration pump will suck an equal amount of the ultrafiltration to be drained through the drain. Actually, how the ultrafiltration pump is working, there are multiple methods, engineering methods I may be mentioned one of them here, but I think as a clinicians we don't need to know more than this. Just the main idea that the hemodialysis machine itself is controlling this ultrafiltration pump to ultrafiltrate here the amount of water that was decided to be ultrafiltrated from the patient.
Before going to the next point, I want to mention an important information that I didn't mention in this chapter, but I will mention in detail in chapter 6, inshallah. About the dialysate flow rate. The dialysate flow rate is about 500 to 800, ranges from 500 to 800 ml per minute. Usually, the dialysate flow rate is adjusted at 500 ml per minute. But is there any benefit from increasing the dialysate flow rate from 500 to 600, 700, or 800? And does this affect the adequacy of dialysis? This what we will talk about in details in chapter 6, inshallah.
So we now prepared what is called the pure dialysate. But what about the preparation of ultra pure dialysate? The ultra pure dialysate is more purification, more step of purification for the pure dialysate. So as we mentioned, this is the water preparation and purificating system, balancing chamber. The pure dialysate is formed and goes through the dialyzer. How to form ultra pure dialysate? This is done by doing an extra step by the addition of bacterial and endotoxin retentive filter, and this filter, ultrafilter, and this is the ultrafilter that we used before and we mentioned in the water unit in the last lecture. As we mentioned, this bacterial endotoxin retentive ultrafilter removes particles between the size of 0.001 to 0.05 micron. This bacterial endotoxin retentive ultrafilter will form the ultra pure dialysate. So what is the difference in the standards of purity of the pure and ultra pure dialysate? Regarding the colony forming unit, the pure dialysate is accepted to have colony forming unit less than 100 and the action level is more than or equal 50, and the endotoxin units less than 0.5 and the action level if the endotoxin units are more than 0.25. But the ultra pure dialysate, in the ultra pure dialysate, the colony forming units of bacteria are more or less than pure dialysate and also the endotoxin units. The ultra pure dialysate colony forming units of bacteria are less than 0.1 and the endotoxin units are less than 0.03. So this is more pure than the pure dialysate. So is there an evidence that the ultra pure dialysate is better for our patients to be used than the pure dialysate? The answer is yes. There are multiple evidences that show that ultra pure dialysate decreased the C-reactive protein and interleukin 6 plasma levels. Ultra pure dialysate improved response of anemia to erythropoietin therapy. Ultra pure dialysate helps to have better nutritional status, reduce the plasma levels of beta-2 microglobulin, residual renal function loss is slower, and finally, the cardiovascular morbidity is lower with the use of ultra pure dialysate. And the ultra pure dialysate use is now highly desirable for hemodialysis, especially with the use of high flux dialyzers nowadays, as these high flux dialyzers, with the use of these high flux dialyzers, there is an increased risk of contamination being drawn from the dialysate into the bloodstream because high flux dialyzers have high permeability. So if there are endotoxins and the colony forming units in the dialysate, they will pass to the patient. So although the pure dialysate here have low bacterial count and endotoxin units and is not causing pyrogenic action, they may contribute to chronic inflammatory response, which may cause long-term complications in our patients. That's why the use of ultradialysate is better, and it is confirmed that it has many advantages over pure dialysate. The next point that we want to talk about dialysate is the carbon dioxide production during hemodialysis and what is called dialysate-related acidosis. We know that dialysate and dialysis is an indication for patients with metabolic acidosis. So, how dialysate and dialysis can cause acidosis? Let's see. Normally, during hemodialysis, carbon dioxide is formed inside the hemodialysis machine when the machine mixes A concentrate with B concentrate. When A concentrate mixed with B concentrate, the bicarbonate in B concentrate will mix with hydrogen in A concentrate and form the carbonic acid, which will be divided into carbon dioxide and water. So inside the hemodialysis machine itself, carbon dioxide will be produced within the dialysate itself, and this carbon dioxide will diffuse into the patient's body. Also, some bicarbonate will diffuse directly through the hemodialysis machine. Some of the bicarbonate will not mix with hydrogen. So, some of the bicarbonate in the B concentrate will mix with hydrogen and form carbon dioxide, and some of them will not mix with hydrogen and diffuse into the patient directly. And in the patient, the bicarbonate will mix with hydrogen and again forming carbonic acid, carbon dioxide, and water, and this will increase the carbon dioxide load in the patient. But if the patient has no respiratory problem, this carbon dioxide will be exhaled and there is no problem. And this is how bicarbonate will buffer the hydrogen. In the patient is acidotic. Bicarbonate will bind the hydrogen, form carbon dioxide that will be exhaled. But the problem will be present if the patient has respiratory problem. The carbon dioxide that is formed in the dialysate and diffused to the patient, and the carbon dioxide which will be formed inside the patient body will be accumulated because the patient has respiratory problem as COPD, the patient has congestive heart failure with respiratory dysfunction, and this accumulation of carbon dioxide will reform hydrogen and cause acidosis. This is why it is advised in these patients with respiratory problem to avoid high dialysate bicarbonate, to avoid this diffusion, and to avoid the formation or decrease the formation of carbon dioxide within the dialysate. So it is advised in these patients to avoid using high dialysate bicarbonate and to avoid rapid correction of acidosis in these patients to decrease the carbon dioxide load and production. And this is how dialysate can cause acidosis in patients with respiratory problem due to accumulation of carbon dioxide in their body, and this carbon dioxide will reform hydrogen again. The next point and last point in this lecture is the dialysate circuit related alarms. 4 alarms are related to the dialysate circuit. The first one is the conductivity alarm. This is the site of the conductivity monitor in the dialysate circuit, as we mentioned before. The main idea of the conductivity monitor that the flow rate of any electrical current through a solution is directly proportional to the concentrations of electrolyte, in this solution. So in the conductivity monitor, there is an electrical current that passes through the dialysate, and this flow rate is measured. And the flow rate of this electric current is directly proportional to the concentration in the dialysate, and the most important ion of this electrolyte is sodium. So the conductivity of the dialysate, which means the flow of electrical current in the dialysate, is directly proportional to the amount of sodium in the dialysate. So with high sodium, the conductivity will be high because of high conduction and the flow rate of electricity, and if the conductivity is low, and if the sodium is low, the conductivity will be low. The accepted range of conductivity is 12 to 16 millisiemens per centimeter. This is the normal accepted range of dialysate. Actually, or roughly, the conductivity of the dialysate is 10th the concentration of sodium in the dialysate. The conductivity is 1/10 the concentration of sodium. For example, if the sodium concentration is in the dialysate is 135 milliequivalent, so usually the conductivity will be 13.5 millisiemens per centimeter. This conductivity monitor will monitor the conductivity of the dialysate, and if the dialysate conductivity is out of the acceptable range, the bypass valve will act, and this dialysate will go through the bypass circuit to the drain, and this dialysate will not go to the dialyzer. So this is a function of the bypass valve and the bypass circuit to bypass out to the drain the dialysate with non-acceptable range of conductivity monitor. So what can affect the conductivity? What makes the conductivity high or low? We mentioned that low conductivity is usually due to low sodium concentration in the dialysate, so the dialysate is hypotonic. What may cause a hypotonic dialysate? First of all, you are using incorrect concentrates. There is a problem in the concentrates that you are using. Or the concentrate canister is empty. The A concentrate is empty. So the mixing ratios are deviated. Or the concentrate line, this line is not dropped well into the canister itself. Or this line is kinked and it is not taking appropriate ratios from the concentrate. Or if there is air in the acid or bicarbonate lines, or if this proportionating pump is running too slow, so the delivery of sodium to the dialysate water is low. What are the adverse effects from having low sodium in the dialysate? Now you have hypotonic hypoosmolar dialysate that will cause low blood pressure, muscle cramps, and all other hyponatremia sequences can affect the patient. What may cause high conductivity? High conductivity is present due to high sodium concentration in the dialysate. So you have now hypertonic dialysate. What can make high sodium concentration in the dialysate? First of all, the incoming water from the water unit is untreated. There are impurities and contaminants in the water coming from the dialysis unit, water unit, which may contain sodium more than usual. The second, that may cause high concentration in the pure dialysate here, the water supply coming to the hemodialysis unit is interrupted. The water coming from the water unit is slow flow. So a small volume of water reaches the portionating system, which will make a higher concentration of sodium. The third point that may make high sodium concentration in the pure dialysate if the portionating system is working too fast. Or finally, if the acid or bicarbonate are not mixed well. Okay, this may lead to high sodium concentration. What are the disadvantages of having hypertonic hyperosmolar dialysate? So this will infuse more sodium into the patient, which will cause increased thirst and will cause other consequences of hypernatremia that may appear on your patient. The next monitor that we will discuss is the temperature monitor. Where is the site of the temperature monitor in our circuit? It is here. The accepted range of the water temperature is between 35 to 38 degrees centigrade. And if the water or if the dialysate coming through the temperature monitor is out of this range, again the bypass valve will act and the dialysate will go through the bypass circuit to the drain and it will not reach to the dialyzer. What are the problems if we have a dialysate with higher temperature or lower temperature? A dialysate with low temperature, the patient may feel cold, there may be shivering and discomfort. And with high temperature dialysate, this is very harmful. It may cause severe hemolysis, protein denaturation, and may cause cardiopulmonary arrest. The next detector or monitor is the blood leak detector. This is the site of the blood leak detector. Normally, the dialysate is going through the dialysate compartment in the dialyzer and the blood in the blood compartment, and actually there is no mix between dialysate and the blood. It is not normal to have blood in the dialysate outflow. The dialysate outflow must contain only dialysate. So the blood leak detector will detect any blood coming out with the dialysate. The question now, what may cause blood coming out with the dialysate? This can occur if there is ruptured dialyzer fibers. So if there is ruptured dialyzer fibers, some of the blood will mix with the dialysate and it will go out with the dialysate in the dialysate outflow and it will be detected by the blood leak detector. And the machine will alarm and the dialysis will be stopped. The blood pump will be stopped. But there is important point that there may be false blood leak alarm. The blood leak detector will act, but there is no blood in the dialysate. This may occur if there is air bubbles in the dialysate, deposits of grease or scales on the sensor here that read the blood or detect the blood in the dialysate. And there are many case reports that blood leak detector can give false alarm in patients who received hydroxycopolamine infusion. To diagnose false alarm, you can use the hemostasis strips that detect hematuria in the urine. You can use them by dipping them in the outflow dialysate. If these strips detected blood, so the dialyzer must be changed because this means that there is actual blood in the drain and the dialyzer is ruptured. And if these strips doesn't detect any blood, so you have to clear the blood sensor or search for the cause, clear the blood detector sensor from the scales or grease, or search for the cause why the blood leak detector gave this false alarm. Our last monitor alarm is the pH sensors. The pH sensors is for the detection of the pH of the final pure dialysate, which is usually, we mentioned, between 7 and 7.4. The pH sensor actually is not present or not famous to be present in all hemodialysis machines, but certain machines are equipped with this pH electrode as part of the proportionating system. The primary function or purpose of this pH electrode is to ensure that the correct concentrates are connected to the machine by identifying any deviation in the abnormalities. For example, the sensor will alarm that the pH of the dialysate is abnormal. For example, if the B concentrate is not connected to the machine, for example, or even if the A concentrate is not connected to the machine. But actually, the pH sensor is not famous or is not common in most of the hemodialysis machines. And we come to the end of this lecture. We talked and discussed in the past 2 lectures or the past 4 lectures about the blood extracorporeal circuit, the dialysate formation. Now the dialysate and the blood will go through the dialyzer. So our next lecture will be about dialyzers overview. See you in the next lecture.